Can everybody hear me up there? Are we good? All right. So we still making our way through the Chomsky hierarchy. Last time we talked about languages which are recognizable and decidable, and we showed some closure properties of them. Today I want to switch gears a little bit, talk about an interesting and fun topic, computational universality and the Church-Turing thesis. What is possible to compute and what isn't? In the terms of the book, it's chapter 3, pages 137 onwards. It's kind of an independent topic of some of the other stuff. It's orthogonal, but it's still very good for you to know and think about these things. So the idea is that many types of systems can perform arbitrary complex computations, and they're equivalent to each other. So we've already seen grammars that can essentially compute. If you switch to context-sensitive grammars, they're as powerful as Turing machines. We'll talk more about that in a later lecture, about the details of that. But arbitrary grammars can simulate Turing machines. Turing machines can do everything we think we know is computable. Lambda calculus, founded by Church. In fact, Turing used that to make the jump into Turing machines and show they're equivalent. Anything that you can do with a grammar, you can do with a Turing machine, you can do with lambda calculus. You can also do with so-called post-tag systems, mu recursive functions, cellular automata like Conway's game of life. How many heard of Conway's game of life? It can do arbitrarily complicated computation. You can run Unix on Conway's game of life. It won't be simple, it won't be easy, it won't be streamlined and necessarily efficient or anything like that, but the point is it's possible to do that. And of course you can do arbitrary computations with Boolean circuits. You all know that if you took logic design. In fact, that's how our actual computers these days are implemented, using AND, OR, and NOT gates and other logical Boolean circuits all juxtaposed to form arbitrarily complex computations. We already saw that you can use the Fontine equations polynomials specifically to do arbitrary computations. That's Matiashevit's solution to Hilbert's 10th problem. DNA computers work really well. How do we know? We'll look in the mirror. You are one. We are all ones. DNA computers. So that doesn't use silicon at all. It doesn't use electricity in the conventional sense. But it's very, very effective. It's highly parallel. It's very robust types of computations. And these are all equivalent to Turing machines. And there's lots of other novel ways to compute besides the ones I'm listing here. So for example, the game of billiards could be used to compute arbitrary functions. How many knew that? Yeah, pool, billiards. So let me show you a little later how that's done, but you can have a universal Turing machine doable in 2 states and 3 symbols. And Stephen Wolfram famously put a bounty on this problem, whether there's such a small 2-state, 3-symbol Turing machine. The answer is yes. It was an open problem for many decades. An undergraduate solved it a few months. Once there was a bounty on that problem for, I guess, it was about 25K. So it's amazing. Once you put a bounty on a problem and crowdsource it, amazing things happen. And that's the universal Turing machine right there. It's a 2-state, 3-symbol. It's the smallest machine possible, Turing machine possible, that can do arbitrary computations. Compute any function you want based on the input that you give it. Okay, so it's like a super compiler, except it's tiny. That's the whole thing right there. So that's how small arbitrary computations can be in terms of states and symbols. You can also construct computers from Lego bricks, and you can construct them from Meccano or Vector sets, children's toys. And this will perform arbitrary computations if you make them complex enough and add enough moving parts and so on. You can make a computer out of Tinker Toys, and MIT students done exactly that. They constructed a Tinker Toy computer made of little blocks of wood that plays perfect tic-tac-toe. You can sort of see the configuration of this 3x3 board here, and it's kind of a hint as to what it does. But you can use Tinker Toys to do arbitrary computations. You can use nuts and bolts to do arbitrary computations as well. So here's a nuts and bolts computer when a NOT gate inverts the input by rotating a bolt the other way, and they're spring-loaded and so on. 2 plungers against 1 plunger is an OR. How many can see that? It's an OR gate. If one of the plungers is pressed, the output plunger is pressed and only takes 1. You can put an AND gate together with nuts and bolts by using de Morgan's law. Now that you have an OR and a NOT, you can construct a NAND and an OR and any other gates that you want. So strictly speaking, from nuts and bolts, you can build an arbitrary computer that will compute arbitrary functions. right? Just take the blueprint of the CPU and implement it using nuts and bolts. Now, I'm not saying it'll be fun or streamlined or small or efficient or cheap. But that's not the point. The point is it's possible to do, right? There's lots of ways to compute. You can compute it with water pipes. So you can construct a transistor out of a one-way valve here and a faucet type appendage. In fact, a faucet, a kitchen faucet, is a water transistor. How many get that? A faucet is a transistor. You apply some force at one point of the pipe using the faucet knob, and that blocks or unblocks the flow, and that's what a transistor does exactly. And a one-way valve is a diode, and you can construct capacitors. A resistor, for example, in a water pipe is just a constriction in a water tube or in a water pipe. So now that you know how to build circuits out of silicon and electrical engineering parts, they are the water part analog, the water pipes analogs. And using this simple mapping, you can construct arbitrary computers from water pipes and water flows. So if I give you an arbitrary configuration of water pipes and ask you, does water ever come out of this particular specific pipe that I'm pointing to at the very end of this giant water pipe configuration, how hard is that problem to solve computationally? What would you guess? You think there'll be an efficient polynomial algorithm or even an inefficient exponential time algorithm, whether water is going to come out of one of the tubes when I give you a big configuration of water pipes, arbitrary configuration? It would be undecidable. How many get that? Because water pipes can simulate arbitrary computers. So in general, the problem of whether water will ever drip out of this pipe, there's no algorithm in the universe to solve it, which is kind of amazing. I mean, it's one thing to say that about arbitrary large pieces of code, but to say that about a bunch of water pipes connected together with T-sections and faucets, and I mean, that's unbelievable almost, except that it's true. So computation and computational universality is ubiquitous. It's everywhere around us. It's hard to get away from it, actually. It's not hard to construct computers. It's hard to construct something that isn't a computer, actually. That's how ubiquitous the phenomena is. We didn't know all that until Turing. We thought it's really, really difficult to construct something that does arbitrary computation. In fact, it took us thousands of years to get to that point, right? From prehistoric times up to way to, say, Babbage. And then electronically, we repeated that feat, in the 1930s and 40s with van Neumann and Turing, and made that much more efficient. But computers were still the size of this room. Nowadays, we repeated that feat one more time, even more efficiently, even more thriftily, even more cheaply and cleverly, and now they're sitting in our pockets. These very same computers that used to be the size of this room, requiring a megawatt to run and 30 people to operate, now they're called smartphones. And soon, there'll be tiny little chips in your cranium. Some people are actually already walking around with chips in their heads. How many knew that? It enables them to, say, move when they had some disability, or enables them to see if they were blind. You connect the camera directly to the visual cortex using this processor, and you can completely bypass the retina and the eye and anything that might be not working properly in between. And so you don't need eyes to see, right? Just like you don't need keyboards to compute, right? Just like you don't need screens to compute. Just make it more convenient, but it's not the essence of computing, these things. So there's a blueberry muffin computer. This one is a bit of a humorous example, but this implements a Turing machine that recognizes the language that's palindromes. W is equal to WR. This blueberry muffin computer recognizes the language WW. It's not even context-free. But anyway, here's back to billiards. I mentioned billiards. So billiards is computationally universal. So here's a billiards configuration that simulates an AND gate, and it's pioneered by Richard Feynman, who first came up with this example. I guess he was a billiards fan. So another implementation is this gate here. So if two billiards balls come through these two holes, the input 0 and the input 1, two billiards balls simultaneously enter this contraption. It's basically a bunch of bumpers, you can think about it, on the billiard table. If they both enter simultaneously and collide, one will come out of here and the other will come out of here. The inelastic collision will happen right at this point. But if one of them is missing and one just comes in and doesn't encounter the other because it's not there, it'll go right through and the other one will go right through. So in some sense, it'll come out of this particular hole if and only if both of them simultaneously occur at these two entrances. And this exit will be sort of the AND of these two inputs logically. And now you have a little primitive AND gate made of billiard ball collisions. How many get that? So if you start compounding that together and with lots and lots of other gates and OR gates and NOT gates, you can have arbitrary computations implemented on the top of a billiards pool table. Now, let's get it straight. The table will have to be very large. You'll need lots of billiard balls. And you'd have to sort of ignore errors and friction and, sort of an ideal simulation type of scenario, ideal physics simulation, a frictionless surface and so on. But the point is, billiards can simulate arbitrary computations, right? A bunch of billiards balls colliding and moving around and bouncing off the walls just according to the laws of Newtonian mechanics. Simple inelastic collisions and so on. Angle of reflection is the same as angle of refraction off bouncing of ball off a wall and so on. And pool is undecidable now. So if I ask you the question, will a certain ball will ever reach the corner pocket in general, that question is undecidable. How many get this? Because you're talking about arbitrary, complicated simulations given enough balls, a large enough table, and complicated enough initial conditions where the positions and velocities of the balls are set at time 0 at the beginning of this simulation. Again, we didn't know all that. We thought it's hard to build computers. It's hard to get away from computers and computations. It's everywhere around us. And by the way, now you know why pool, and yet one more reason perhaps, it's not the only reason, why pool is so interesting and challenging of a game. It's hard to get good at. It's undecidable what these balls will do in the long term given enough collisions and enough balls. Okay, any questions about any of that? So it's not just pool that's undecidable, it's Newtonian mechanics that's undecidable, because Newtonian mechanics and collisions is the basis of pool and everything else around us, orbital mechanics and so on. And speaking of orbital mechanics, we all heard of inverse square law of gravity, right, discovered by Newton in the 1600s. So n-body problems, when there's only n is equal to 2, it's simple. You have ellipses or circles, which are a special case of ellipse. A planet revolves around the sun or a moon revolves around the planet. No big thing, but that's a very simple example. You have multiple moon systems. Again, they move in ellipses more or less. They slightly perturb each other. But there's much more complicated computational interactions among planets, gravitational interactions that can be interpreted as computational interactions, right? You can have a two-body system that revolve around each other like this. A third one will come in, replace one of the ones that are there that will be ejected, and the other one will be ejected to infinities, and the other two, the new one plus one of the old ones, will keep rotating around each other. This can happen, actually, and does happen in space. And that's much harder to predict than just simple ellipses. So for centuries, we knew about the simple ellipses, hyperboloids, parabola kind of motions, and hyperboloid kind of motions of planets and gravitational bodies. But we didn't know about, for example, this one, a figure 8. 3 bodies in space can rotate around each other gravitationally in a figure 8. How many knew that? It could happen. It doesn't mean it happens left and right everywhere you look. It's an unusual configuration. But the point is, inverse square law of Newton, pure and simple, nothing else added, can result in such a weird figure 8 orbit. And it's a stable orbit. That's important. It doesn't just happen once. It happens repeatedly. All right? And if you change some of the masses by epsilon up or down, or changes some of the velocities of any of these bodies slightly faster or slower, or slightly perturb them in any way, it'll keep doing this, slightly perturbed. So it's a stable orbit. It's not unstable that if you just sneeze at it, it'll fall apart, or these things will fly to infinity. They won't. These are stable orbits. And we didn't know that until just a few years ago, actually. After looking at the inverse square law for almost 400 years, we finally discovered this, just because somebody said, what if, and played the simulation, and it turns out it works. So planetary systems are like 3D billiards, even more complicated than billiards, because it involves 3D and even nonlinear dynamics, not just linear dynamics. It's quadratic kind of behavior in the denominator of the inverse square law. So gravitational systems are chaotic and undecidable. If you want to know if the Earth will ever be ejected out of the solar system and fly into space, undecidable. We don't know if it will or not. We hope it won't, or at least it won't in the next billion years. We don't care much as a species what will happen in a billion years. Most of us, in fact, many of us don't even care what will happen in 50 years. Global warming. But still, it's very hard to predict these things, okay? So we can't take for granted, that just because you have a simple polynomial, even a quadratic polynomial, even just inverse square, you know all about it. And you know all the consequences of it and how things will interact under that rule and get arbitrary, complicated behaviors. And again, that was news to us humans. We thought, linear systems are trivial, quadratic systems maybe a little more difficult, and then finally Matiashevitz solved Hilbert's 10th problem, and we realized polynomials can simulate arbitrary Turing machines, and there's even a universal polynomial that can simulate any Turing machine. That's how complicated polynomials are. Never mind even more complicated functions like sines and cosines and exponentials and inverse tangents and whatever. Those are even worse. I'm just talking about simple polynomials and a simple quadratic even. So just to finish off a few more examples on orbital mechanics. So here's the orbit, the stable orbit that we just showed you a minute ago. Just so you don't think it's a fluke, this one is a stable orbit too, involving many bodies. So it generalizes to arbitrary number of bodies. Now, I'm not saying that everywhere you look in the universe you'll see examples like that. These are rare, and they have to be set up just right, and it's unlikely. But the point is, it can exist, it satisfies inverse square law, and it's stable. If you perturb any one of these things slightly, this whole thing will continue unabated. It won't fall apart. Here's another one where three bodies are moving in 3D without it even being flat. This one is flat. This is in the plane. This is not planar. Still 3D. Amazing. We didn't know this for 4 centuries from the simple inverse square law until just 10 or 15 years ago. And just so you don't think this stops there, here's another one where there's 3 interjoined orbits. Here's 3 different orbits in a different configuration. Here, one of them is like a 888, and one of them is an ellipse, one is a circle. Here, 2 are kind of flattened. And again, I remind you, these all are immediate, simple Newtonian mechanics consequences of the inverse square law of Newton, right there. Okay. So you're beginning to see, how ubiquitous computations are, how complicated it is to predict even simple relations among things, right? And just so you don't think it stops even there, there's 4 bodies interacting like this gravitationally. They don't have to be the same mass, and if you perturb them, it's a stable orbit. There's another one. I'm rotating it so you can see the 3D nonlinear nature of it. Here's 6 interacting like that, right? 2 per plane. And here's a whole bunch of others interacting on, 1, 2, 3, 4 different, kind of circuits, none of which are planar, none of which are even circular or elliptical for that matter. Here, this one I'm rotating so you can see the complexity of it. And it goes on and on and on. Now we have a whole zoo of different families of possible orbital mechanics and so on. And the point is, this is 3-dimensional billiards, evolving very slowly because the distances are great and masses are large. But the whole universe is computing gravitationally, just like the game of life of Conway is computing using a cellular automata. So whether one of those celestial bodies will eventually fly out of orbit or collide with another body or fall into its sun or whatever, undecidable, even though it's just a simple quote-unquote, inverse square law. Okay, any questions so far? Yeah?
So if you were aware of all the forces that were at play and you were running a simulation, you couldn't say that this is going to destabilize at some point? That's an undecidable question.
Yeah, it's undecidable. Just like you look at a Turing machine, and it's not even about forces. It's all discrete. Things either move left or right. A changes to a B or it doesn't. That's undecidable already. With orbital mechanics, you have that problem, and you have another problem. It's continuous as opposed to discrete quantities. So you have problems of measurement. You can't measure the exact velocity and the exact acceleration and exact position of anything because even if you're a millimeter off or even a nanometer off, the whole thing could either diverge or converge, fall apart or fly apart, or fall together after a certain amount of time, and you don't know which. That's the nature of chaos. It's like the butterfly effect that the scientist keeps talking about in Jurassic Park. How do you know what I'm talking about? The butterfly effect? You've seen Jurassic Park? Butterfly flutters its wing halfway around the world, and 2 months later there's a hurricane in Florida through a whole bunch of complicated sequences of interactions in between. And it's very hard to predict that butterfly causing that hurricane a month later, half a world away. It's hard to simulate that. In fact, it's impossible to simulate that. Tiny, tiny effects make a huge difference, given enough time. right? There's even movies, you know this in real life, right? Chaos, unpredictability, right? You're 1 or 2 seconds late or early, out of your house, and you get to an intersection, and you're 1 or 2 seconds early at an intersection, all of a sudden somebody rams into you. If you were 1 second late or 1 second early, the accident wouldn't have happened. And you wouldn't have to, incur all these bills and be in a hospital, and it changes your life. How many get this kind of example? Yeah, I mean, tiny little differences make a huge outcome difference at the end, very, very dramatically. The military does this all the time. It tries to simulate wars and conflicts and battles and engagements and try to see what would happen. What if we invade this or with so many soldiers and here's the opposing force. Even if you know all their positions and all their forces and where every tank and every armed person is and every plane and all their trajectories, you move a soldier 1 centimeter to the left. So you simulate and you see that you win the battle decisively. So the military says, oh great, we're going to win this decisively, so that gives us more confidence that this will work fine. But you take one soldier and you move it 1 centimeter to the left, you run the simulation again, and the enemy wins decisively the entire battle. That can happen. How does 1 centimeter movement in one soldier can affect the outcome of the entire battle completely diametrically opposed? Well, maybe that soldier was a captain of a platoon, and when he got hit, he couldn't give the next order to advance, so the whole platoon didn't advance. Meanwhile, they didn't provide cover for this whole battalion against that sniper over there, and blah, 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 and before you know it, they got overwhelmed. That's exactly what happens. That's what happens in real life. A chance meeting with a certain person, you have a connection with them, all of a sudden you marry them and you have children, and all these lives change just if you were 1 minute early or 1 minute late to some event or some party or to some walking out the door, either coming or going from some event, whatever. This happens. This is chaos. This is unpredictability. It's very hard to simulate. So this certainly happens computationally as well as in our everyday lives. There's even a movie like that. It's called Sliding Doors. How many have seen that? It's a kind of romantic comedy. A woman tries to get on a train on the way to work. She's 1 second late, and the train door slams before her, and she has to take the next train, whereas it cuts to another scene where she was 1 second early, and she gets on the train, and there she meets some guy, and it's a romantic comedy, so you can guess what happens. And the movie diverges, and it keeps going back and forth kind of non-deterministically between these two storylines, and they're very, very different, dramatically different. Same woman, same guy, different lives. So this could actually be a source of interesting storytelling and entertainment. Anyway, so the Church-Turing thesis, pioneered by Alonzo Church, Turing's advisor back in the 30s. And it's not just the Church-Turing thesis, even though we call it that. It is the brainchild of a lot of people that were hanging out together at the Princeton Institute for Advanced Study in the 20s and 30s. Albert Einstein was there, Church Gödel, of course, Turing. There's Johnny von Neumann. Who is this guy? Yeah. It's Robert Oppenheimer. It's close. These are Los Alamos kind of Manhattan Project kind of guys. This guy is who? The young kid with a T-shirt. Anybody can guess? This is the young Richard Feynman, the Nobel Prize winner physicist. That's Stanislaw Ulam, who co-invented the hydrogen bomb along with Edward Teller. And all these guys were there, so we could have called it the Church-Turing, Einstein, von Neumann, Ulam, Oppenheimer, Feynman thesis, as opposed to just the Church-Turing thesis. But that's a mouthful. Can't say that 4 times fast. So we call it the Church-Turing thesis. But the basic question is, what does it mean to be computable? What does it mean to compute? We know what it means to think. We at least intuitively, we think we know what it means to think, because we think all the time, every day, every hour of every day of our lives. And a human is very good at thinking, and if you augment a human with an abacus, it doesn't change its ability to think if it can do simple calculations with some mechanical or even electronic tool. So it doesn't have to be an abacus. It could be a super fast electronic abacus, which is also known as a computer. So if you have a computer or an abacus, it doesn't change the way you think. It just makes it faster and more efficient. It doesn't allow you to do brand new things that you couldn't do before. You can just do them faster and more accurately, more efficiently, and quicker. On the other hand, we have Turing machines that are very, very simple. Right? You have a set of states, a transition function. You already know what those are. Right? And you've already seen some and use JFlap to play around with these automata and program them and see how they operate. And the Church-Turing thesis says that anything that is intuitively computable, like to a human being, that we think of as doable by a human, can be done by a Turing machine and vice versa. So what Turing machines can do is equivalent to what humans can do. That's what the Church-Turing thesis postulates or states. Okay, and when we say Turing machine, we don't mean just Turing machines. We mean lambda calculus, we mean mu systems, and any other equivalent system to those, like Boolean gates, cellular automata, DNA computations. All these are interchangeable and computable and simulatable by one another. Gravitational systems, billiards, polynomials, each one can simulate all the other ones here, right? How many get that? So they're an equivalence class. But still, on the other side, there's a human. And it's not clear how these will exactly simulate a human, and that's why it's called a thesis and not a theorem. Because we understand most of these pieces on this slide. Right? We know what an abacus is and what it can do and what it can't do. We know what a supercomputer, by the way, that's a Cray 1 from 1976, only like 100th the speed of your smartphone in your pocket, but it costs $10 million. We know what Boolean circuits could look like and what they do. We already talked about DNA computing, cellular automata. All these are equivalent. There's only one thing on the slide that we can't quite quantify what it can or cannot do in some absolute sense, and it's still a little mysterious to us how it all works, because it's the only thing we did not invent on this slide. And you can guess what it is. It's us, right? All these other things are artifacts that we invented, except maybe the DNA part. It's hard to quantify that exactly, but with DNA computers, we can simulate all these other computers, and with these other computers, we can simulate DNA interactions, at least. Okay, so we're not sure quite what it means to think. We have an intuition and some understanding of it. We're not completely ignorant of all the ramifications of thinking or not thinking. But it's hard to quantify, especially when you get into kind of fuzzy, feely kind of human capabilities and abilities and traits, such as music and art and poetry and humor, justice, truth, aesthetics, and so on. It's hard to quantify that, even amongst ourselves. Humans have a hard time agreeing on what is funny, what is humor, what is, so some people will think something is funny, others will think it's offensive, others won't get it at all, and we're all human here, right? So if humans can't agree on what is funny and how to construct a joke and what humor is in general, how do you expect computers to do the same? Okay, so that's why it's not an equality here, it's sort of an equivalence. And it's a postulated equivalence. It's not quite a theorem because one of the pieces is fuzzy and not completely definable and understandable. And so that's why we call it a thesis and not a theorem. Any questions or thoughts about that, comments so far? And all the evidence we've seen so far since Turing and even pre-Turing point out to this equivalence. We've seen no counterexamples to this yet. Right? And computers can do more and more things on a daily basis. Nowadays, they can drive cars, they can, recommend to you movies that you will like, and all sorts of AI systems. And so let's go from the bottom. So things that can obviously be done by computers or algorithms, simple games, tic-tac-toe, Sudoku, simple puzzles. Those you can program in an afternoon or a couple of days. Not that big of a deal. Turing machines can do that. They can solve Rubik's Cubes of all kinds, right? Even big Rubik's Cubes. Maybe at some point I'll bring some of my very large Rubik's Cubes. I have a 11 by 11 by 11, and also I have this one. And also I have a 13 by 13 by 13. If you promise not to scramble it, maybe I'll bring it in and pass it around sometime. But anyway, those that can be solved, there's nothing undecidable about them. It's a discrete space, it's large, but it's easily navigatable, and you can come up with solutions. Positional games like tic-tac-toe, chess, checkers, even Go, relatively straightforward to implement. It's tricky to implement more efficiently, so it's fun to play with, but nothing conceptually difficult about those. The tree, if nothing else, you can construct the entire game tree. And the game tree could be large, don't get me wrong. For tic-tac-toe, it's only 700 and some different board positions, but for checkers, it's like 10 to the 20. For chess, it's 10 to the 50. For Go, it's 10 to the 171, roughly estimated. So it's more than a Google. And so Go we thought may never be played well by computers, but lo and behold, AlphaGo by Google just beat the world champion a couple of years ago. Checkers was proven to be a draw in 2007. We've been playing it since, pre-biblical times, but finally somebody proved that it's a draw. So now in checkers tournaments, tic-tac-toe we knew was a draw. How many knew tic-tac-toe is a draw if you make the right moves? Okay, so it's a very boring game. Now checkers is a boring game. But it's not completely boring because you still have checkers tournaments. So how would you guess now a checkers tournament gets conducted so it's still interesting? Because there's no tic-tac-toe tournaments, right? It'll keep being draw, 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 and everybody would roll their eyes and nobody would pay money to see tic-tac-toe champions play. But now checkers is in the same category. So how could you have a checkers tournament that's still interesting today? Yeah. Yeah, you use randomness. You randomly move the first few moves of each player, a computer-generated random set of moves, maybe 3, 4 moves, and then you let loose the 2 players, and the better one will usually prevail over the weaker one, because the random could give either one the advantage statistically randomly, 50-50, and then you know who's the better player after a bunch of games randomly started by a computer, and then the humans take over. So you can do that, for example. Games that involve chance, like dice, backgammon and so on, that's a little bit different because it involves probability. It's not completely deterministic. It doesn't have complete knowledge of either position because it's hard to predict what the dice will show. But still, computers can simulate that, play it pretty well. You can have all sorts of clever strategies. Famously, in 1997, a computer first beat the world's champion in chess. That's a historic first, 20 years ago. And there's Garry Kasparov, the reigning champion at the time, kind of looking very despondent as he kept losing to IBM Deep Blue. And that gave rise to very, kind of dramatic news headlines like the brain's last stand, like humans are some sort of an endangered thinker species. And one movie came about, chronicling this event called Game Over. No feelings, no fear, no contest. It was very dramatic. Nowadays, you have apps on your iPhone that play grandmaster level chess, ELO ratings of over 3,000 that can beat every single human on the planet. The best player in the world is only rated at about 2850 or so, less than 2,900 on the ELO scale. That's a chess rating scale. Who is the best player in the world for chess right now? Anybody heard of him? Yeah, Magnus Carlsen. Sometimes he pulls pranks by going into Central Park in New York, pretending to be some punk kid, and he sits down with one of those con artists that play chess with you for, $10, and, they don't quite recognize him. He wears the disguise, and of course he beats them hand down, and finally he reveals himself, and they all take a bow, but, chess pranks. Now, a harder game to win was Jeopardy, because that involves natural language and a big repertoire of knowledge and understanding and parsing, natural language and English. And IBM Watson beat the world champions by a lot. Look at the scores here. And that happened just a few years ago, about 7 years ago in 2011. That was harder to do. And even harder than that, Go. Go because the game tree is huge, more than the Google positions. And by the way, Google is more than the number of particles in the known universe. If you take and estimate the number of photons, electrons, protons, and neutrons in the entire known universe, a sphere 14 billion light years in radius, and you do the math and you compensate for the fact that the universe is mostly empty space, there's less than a Google particles in the universe. And so you can imagine how complicated Go is if you try to play it brute force. But in early 2017, AlphaGo by Google beat the world champion Lee Sedol in Go, and it beat him flat. I think it was like 4 out of 5 games, and he managed to win one just barely, and he was happy he won just one even. And it was $1 million pot of money for the winner, so he had very good reasons to not lose his title, not just for honor and self-respect, but for $1 million as well, and he lost. So one more task computers now can do that we thought they will have trouble with. And every day we see more of these kind of tasks that computer can now do that we thought they couldn't do before. And then why am I saying all this? This is all in support of the Church-Turing thesis, that Turing machines, i.e. programs, codes, algorithms, can do what humans can do. And these tasks keep giving way and falling one after the other like dominoes. So it's pretty exciting. Now computers can drive. right? There's a Tesla Model S. It has an autopilot. It's been driving itself on the freeways for over 2 years now, 3 years actually. Not only that, it can go 0 to 60 in 2.3 seconds. So not only it's impressive computationally, it's impressive because you can out-drag race Lamborghinis, Ferraris, and Bugattis. You know, for an electric car, that's amazing. And you know, this shows you a little bit of the autopilot capabilities, hands-off driving, and it's about to go autopilot in the cities. 2005, DARPA challenged the world by offering $1 million to anybody who can come up with a self-driving car that'll navigate about 100 miles of desert roads. How many remember that or heard about that? The DARPA, you know, challenge. And the cars look like this. They were very clunky with all these sensors and all these contraptions attached to them, very kind of kludgy, retrofitted things, and none of the entries won the challenge. 2 years later, they upped the ante to $2 million, and so this was 2007 or so. And finally, 3 or 4 entries won and navigated correctly these desert roads. Very hard to do at the time. Nowadays, a Tesla can do it on arbitrary freeways, hands-free, and it doesn't look kludgy at all. In fact, it looks pretty cool. So, you know, that's my favorite Turing machine. So I had to get my own. And last couple of weeks of the semester, we'll find a date on a weekend where I can bring it in. And if you want to kind of experience the acceleration and see all the cool gadgets on board, it's basically an iPad on wheels. It's pretty nice. We'll have test drives around the block. I'll announce it in advance, and you can see for yourself. Nowadays, you can purchase it for $35K as the Model 3. Has the same DNA as the Model S. And self-driver, autopilot. Pretty cool. So again, this reinforces, again, the Church-Turing thesis. Whatever humans can do, like drive cars now, avoid pedestrians and so on, computers can do too. In particular, algorithms can do. In particular, Turing machines can do. Right? So this cartoon kind of illustrates this trend, things that we thought only humans can do, like pick stocks, process speech, compose music, and now this guy is nervously crossing these off as computers can do more and more things. And you know, look at this. On the wall here, the cartoon is about 10 years old, and on the wall here it says only humans can drive cars. Now that one's on the floor too, as well as many others. And the list of things that humans can do that computers still can't do is getting shorter and shorter and shorter. And at some point, it will vanish. And there's already many things that computers can do that humans cannot do. And not just for speed. Right? A computer can add up 1 billion numbers in 1 second. Now, a human can't do that. So we're not talking about speed. We're talking about what is possible, speed aside. Right? Computers can do all sorts of amazing things that humans cannot hope to do, certainly not in our lifetimes. Right? There's not enough time. Now, you know, so there's a lot of questions about what is intelligence, what is consciousness, what is mind, what is self-awareness, can computers do all that? Well, we can't even define that very well among ourselves, us humans. So, you know, it's not fair to try to claim that computers can't have these things that we can't even define for ourselves, right? You know, an intelligence, a mind, a self-awareness, a sentience could be simply an emergent property of a very complex system, right? Certainly it seems to be the case about us, you know, with all of our, you know, trillions of cells kind of and neuron firings kind of going on in high parallelism. So we still don't know where the end point of all this is. We're still at the very beginning, the initial tail of this trend that's growing exponentially, like Moore's law. Moore's law is not the only exponential that's growing exponentially. There's dozens of other things that are growing exponentially too, and at some point we'll talk more about that and the technological singularity and other cool things. But simple things like digits of pi, we can compute those algorithmically. There's nothing mysterious about those. Those, you know, these are kind of Ramanujan type identities that describe 1 over pi. It's not an approximation to 1 over pi. It is 1 over pi. And Ramanujan would just write those down out of the top of his head, one of the best mathematicians of the 20th century, early 20th century. Prime numbers, we already talked about that a lot. You can compute them by Sievert-Verstaessanis. There's a 2,000-year-old algorithm, one of the very earliest algorithms we actually know. And as theorems, you can prove about primes as little prime open problems, largest known primes. Those you can compute with enough brute force, nothing too We can compute, graphics, harmonics. You can compute visualizations. This is a 4D tesseract, four-dimensional cube rotating. It's rigid. It doesn't look it, but it is a rigid four-dimensional object. Anyway, we can compute all sorts of cool graphics, images, and morphing, and things that we have trouble with. So I've just listed a long list of things that we can compute easily, simple algorithms, not necessarily efficient algorithms, but most of them are. Things that we have trouble computing is things like humor. Humor, it's hard to codify. You can't easily write a computer piece of code that will tell you what's funny and what's not funny. In fact, humans will argue about that. Often you see, jokes that some people will laugh at, other people will be offended at, and other people will just shrug their shoulders and not even understand. So things that are fuzzy to us, it's hard to even begin to find how to teach it or get a computer to do it or do it well. So these cartoons kind of make light of the computability or lack thereof of humor. Things like emotions, love, hate, revenge, justice, fairness. It's not nothing, but it's very hard to codify, right? And what's the square root of love, right? I mean, that's kind of a silly question. So try to teach that to your code. Difficult. But it's not nothing. It is fuzzy. It's hard to define for us humans. But our entire world, our entire societies operate on these principles. And every movie, every novel, every play ever written, has some component of these emotions. Love or hate or revenge or truth or justice or fairness or cruelty or whatever. It's not nothing. The whole world runs on these things through us humans. And, but there's no reason to think one day codes and programs and neural nets and AI and deep learning systems could not exhibit some of these behaviors at least. And you can ask, well, does the behavior imply the actual phenomena? But if it's indistinguishable from the actual behavior that's induced by the actual phenomena, how is it really different if it's not distinguishable using all possible external tests like the Turing test and so on? Right? So, if Terminators can look arbitrarily like humans, and, Neo in the Matrix is a good example. He lives in this simulation, but he doesn't know it because the simulation is so good. Right? How many have seen the Matrix movies? And he wakes up and he realizes, oh, crap, it's a simulation. And then a whole bunch of things ensue from there. So if the simulation of something is so good and high fidelity and accurate and behaves exactly like that thing itself, philosophically, is it really distinguishable from that thing? And people, philosophers can argue about that and have argued about that for centuries, in fact, not just decades. Weather systems are a little bit different. They involve a lot of chaos and insufficient data, and undecidability is there, but also you don't know all the positions of the particles and all their velocities at any given moment. And by the way, this is Hurricane Gustav crossing over Cuba towards Florida in 2008, and many people died from that, and as they do in every major hurricane. So we have a high incentive, there's tens or even hundreds of billions of dollars of property damage. We have very high incentive to try to predict whether a hurricane will come and how strong it'll be, what its path will be, whether it will make landfall. It's not like we don't care. We care a lot, but it's very, very difficult to do. And not only it's undecidable, even if we knew all the positions and particle motions and speeds and velocities and energies, even if we do know them, it's still undecidable. And we don't even know them, because you can't measure all these things over a very large volume of space. Even to within a granularity of a cubic mile, it's hard to measure all these millions of cubic miles all over the place, including up into the sky, because it's a 3D model. So you have chaos rearing its ugly head over and over again in these phenomena. There's the 2004 tsunami that hit the shores of India and Sri Lanka and some of the South Asian countries, and it left almost 250,000 people dead. And that's what it looked like at ground zero on some of the beaches. Probably most of these people did not survive this image. Maybe they found the camera after the fact. Almost 10 teratons of energy came rolling, not gigatons, but teratons, 100-foot waves, and if we could predict this kind of things, we would. We would really like to be able to predict that, compute that, calculate that, and anticipate these things. Very, very difficult. Again, you have undecidability at the very core, because these are just complicated computational systems of interacting particles, 10 to the 30, 10 to the 40 particles in a large geographic kind of system like that. You have insufficient data. You can measure things, and if you could measure every single particle and stress point and velocity and temperature at every cubic angstrom in this entire space, you'll still have undecidability on top of that, and you can't even do the measurements correctly. And of course, it gives rise to chaos, high sensitivity to initial conditions. And so this is sort of the limit of what we can do. We can't do these things. And there's good reason to think that we can never be able to predict these kind of events in the universe, if for no other reason for their undecidability underlying properties. And we already saw from Rice's theorem that most properties of formal languages are undecidable, right? How many remember that from last time? Rice's theorem, almost everything is undecidable. We proved that. And certainly these things are undecidable. And it doesn't stop at properties. So this is not a corollary of Rice's theorem directly, but Rice's theorem is just the tip of a giant iceberg. And Rice's theorem is already pretty dramatic, saying almost all properties except two of recognizable languages are undecidable, but many, many other things are undecidable too, not just properties of languages. Questions about computations and algorithms and physical systems, whether it's gravitational systems, weather systems, tsunami systems, earthquake systems, human behavior systems, economic systems, financial systems, political systems. If you find it surprising that political systems are hard to compute or predict, look what happened 2 years ago. All the experts were wrong, and they had that high incentive to predict elections correctly. So even things like protein folding, the formula of a protein, there's no mystery about it, but how it folds on itself at a tertiary structure, we have no efficient algorithms to compute that. You can do it brute force if you enumerate all possibilities, and I suppose there's probably only a finite number of possibilities if you account for stable, discrete configurations. But even that problem is, we don't have a good solution for yet. Question?
So the crowdsourced project, folding at home, is that how is that possible that you can't accurately determine?
Yeah, how is it possible to do protein folding at home? There's this SETI at home that checks for extraterrestrial signals. So crowdsourcing computations to a large bunch of people, it's basically luck. If a lot of people try a lot of things, and you look at the things that worked, and you classify them by goodness, like minimization of the energy of the entire molecule or whatever with the electrostatic forces, you can sort of have a top 10 number of candidates for the possible solution. You won't know for sure that there's no better solution, but you'll have some pretty good solutions. In everyday life, we solve complicated problems all the time in a heuristic kind of a way, not necessarily exactly finding the best solution. Now, you look for a job, you want to maximize your income, you go for a bunch of interviews, you get a bunch of offers, you play both sides against the middle, start a bidding war over yourself, and finally you take the position with Google. How do you know you maximize your salary? Maybe you did, maybe you didn't. You increased it quite a bit from what it was on average if you just took a random offer. So in real life, we kind of do this all the time. And things like SETI at home or folding at home, or many other kind of at-home kind of crowdsourcing computational tasks, basically do it heuristically. A bunch of people trying a lot for a long time, and you look at their results, and chances are you're pretty close to optimal, but you don't know. It may not be the best solution. There's two galaxies colliding, each one containing 100 billion stars. This collision is shown here in about 2 seconds, but it takes 1 billion years for the collision to unfold. In fact, our galaxy right now is in the middle of a collision with another galaxy. The collision has been happening for a couple of billion years now. How many realize that? We're in the middle of a collision right now. The stars are so far apart, the solar system is so far apart in these galaxies that two galaxies can collide and pass through each other and warp each other like this without any two stars colliding with each other, because it's mostly empty space. Anyway, very hard to predict the dynamics of such a system. And of course, on a smaller scale, you can't predict lightnings and thunders and weather systems in general. Turbulence, notoriously hard to compute. There's turbulence in a cup, and it's a function of temperature, but also there's chaos and sensitivity to initial conditions. There's the Navier-Stokes equations of fluid mechanics. We know what these equations are precisely, but it's very hard to predict their consequences. And you can have, whenever you pour coffee into a cup, you get chaos. You get turbulence, which is a liquid form of chaos. If the flow is laminar, like in this nice two-dimensional system, that is easy to compute. There's no turbulence, no chaos there. But even if you have a cone in a slipstream of air around it, or water for that matter, you get these turbulent behavior, and that's very hard to compute, very hard to predict. Chaos, arises very, very quickly. And also you have insufficient data of all the particles. And even if you did, it's undecidable. And so it's problem on top of problem in a way of predicting phenomena, whether they're in a small scale or a large scale. Right? Even a dripping faucet, it's almost impossible to predict when exactly the next drop will happen and what its shape will be and whether there'll be a little droplets after that and so on. And there's a much larger system of fluid dynamics. This is Jupiter. And there's been a storm there on Jupiter. This storm right here, it's basically a hurricane. It's many times bigger than the Earth, and it's been ongoing for millions of years, the same hurricane, flowing chaotically and irregularly and without regular patterns. But very, very hard to predict if this hurricane will stop in 1,000 years or even in 10 seconds from now. Very hard to predict that. And this is sort of the macro level example of coffee, cream in a cup, or dripping faucet. It's all fluid mechanics, but turbulence is in all of these systems. Yeah, and there is the Navier-Stokes equations in differential form. They look deceptively simple, right? There they are. And these equations predict waves. That's, two-dimensional waves like that is one solution. And they also predict, three-dimensional waves. But in reality, it's very hard to predict these kind of waves from these equations, even though these waves here are inherent in these set of equations. And just to give you the scale of these waves, there's a surfer right there. He's probably a few seconds away from having some bad experience here. Or maybe not. I don't want to underestimate this person. But there's the equations and there's the phenomena, and one is not the same as the other, conceptually, in terms of consequence, certainly in terms of elegance, beauty, cool factor. If you didn't see these pictures, it's hard to believe that these pictures are extractable from these differential equations, but they are. So these equations are the complete description. But getting from here to here is computationally very, very difficult, in fact, impossible, because it also involves chaos and undecidability and other things. And by the way, the Navier-Stokes equation are part of the Millennium Prize $1 million bounty on a bunch of problems, and one of them is NP equal to P, right? And there's a Navier-Stokes equation. One of them was already solved by Perelman about 10 years ago, the Poincaré conjecture. He refused to take the money, right? I think I mentioned that before. He also won the Fields Medal for solving one of these 7 problems, this one, and refused the Fields Medal, too, the first time that ever happened. And again, this all goes back to David Hilbert and his famous list of 23 problems that we talked about. And just kind of, so I'm showing you sort of the cusp of, the kind of the nether region of between what is computable and what is not computable. Pendulums, simple pendulum, assuming no friction, very simple system. You have a double pendulum, a pendulum connected to a pendulum, you get chaos, unpredictability, undecidability, and the motion of this is not computationally computable, actually. And if you have a triple pendulum or even more complicated, forget about it altogether. But even a double pendulum, this is where chaos arises. Single pendulum, completely ordered, not much interesting happening, just back and forth. In fact, that's why clocks are made with a single pendulum, these grandfather clocks, because it's so predictable. That's why they're not made with a double pendulum, because that will not keep time. In fact, you have no idea what it would do. So the question of whether this second green ball will ever go way over the top like that, here I'm tracing the pendulum so you can see how chaotic, non-repetitive the path is. Whether the green ball will go over the top and loop the loop, undecidable, amazingly enough. And that gives rise to fractals. And fractals is a very rich field involving fractional dimensional objects. You have Julia curves. You have fractals in nature, right? Self-similar curves that are hard to get an analytical handle in, hard to compute, hard to even recognize when you see them. Snowflakes, cracks, lightning bolts, crystal growth, they're all fractal in nature. Any questions about this? Feel free to ask questions. I don't want to just go on and on if you're curious about other things while we're talking. Coastlines, so it goes from a very small, like crystal growth, molecular crystal growth, to very large entire coastlines that have kind of fractal geometries. And fractals have a lot of applications in movie making, graphics, and understanding anatomy. Your blood system, your capillaries and veins and arteries form a fractal network, actually, inside your body. So is your nervous system. There's a fractal dresser, furniture made of kind of fractal-like geometries. I think that's pretty cool. You know, fractal tattoos. I don't recommend that you get one, but there's even fractal antennas. Your cell phone has a fractal geometry to the internal antenna inside your smartphone. How many knew that? Why would you want a fractal geometry to the antenna that looks like this as opposed to just, or even like that? That's another fractal geometry for an antenna, as opposed to just a piece of wire or a coil. Yeah. Yeah, because the antenna has to be geared to the wavelength of the signal that it's supposed to receive. And so you need one kind of scale antenna for very high wavelengths and larger antennas for larger wavelengths and tiny antennas for very short wavelengths like Wi-Fi signals that run in the gigahertz range. And so you need a whole bunch of different antennas if there were separate antennas. But if the antenna has a fractal geometry like this or even like that, it can receive different signal wavelengths with the same single antenna and pretty efficiently, and it's very compact. And so there's a whole company called Fractal Antennas. I'm not making this up. Yeah? And they produce antennas for cell phones and lots of other cool technologies. Right? They produced a cloaking device. Right? Captain Kirk once tried to steal the cloaking device from the Klingons back in the 1960s version. He masqueraded as a Klingon or a Romulan, I guess. I guess it was Romulans. How many even know what I'm talking about? Cloaking. Good. Some Trekkies in the audience. And it was a hypothetical device that can cloak, an entire spacecraft. Of course, Harry Potter, not to be outdone, had a cloaking kind of coat that he could wear, and it would kind of cloak him out. And sure enough, we started building cloaking devices for reals. Now, they only operate in certain wavelengths, but the object in the middle of them will become invisible in that wavelength, because the wavelengths will be routed around by the geometry and chemistry and physics of the object, and it'll pass the light right through in the same way as if the object wasn't there, which means it's effectively invisible to you. That's what invisibility is, right? The stuff that's behind an object appears to you as if the object wasn't there. Now, whether the object is there or not at that point is irrelevant. You can't see it anyway, because you're seeing what's behind it instead. So we have cloaking devices now, and they're beginning to work in more and more frequencies. And so one day you may have, the Romulan cloaking device or some sort of a Harry Potter kind of a thing. Maybe not as ubiquitous and as general as that, but still, we're getting there. And of course, you have Mandelbrot sets. Again, this is stuff that's computable, but undecidability and chaos, kicking very quickly. And the Mandelbrot set is a very simply defined object. To define the Mandelbrot set, basically it's a one simple recurrence, simple, quote unquote, it's one simple quadratic recurrence relation. Take a point in the plane and keep running it through this iteration. Square it, add a constant, square the result, add a same constant, square the result, add the same constant. If that point diverges to infinity, it's outside the Mandelbrot set. If it doesn't diverge to infinity, it's inside. The Mandelbrot set is simply the set of all points that converge as opposed to diverge when you repeatedly apply this squaring operation in addition. That's it. That's the entire definition of the Mandelbrot set, yet it's thought to be the most complex object in all of mathematics, and that says a lot. There's some really complicated objects in mathematics. And if you zoom in arbitrarily large, you see more and more copies of the set itself deformed, and there's an infinite number of copies, uncountable infinite, in case you were wondering. Question? Why do you see them in nature? Because nature has a self-assembly kind of aspect to it, or tendency to it. It self-assembles, and as you assemble things from smaller units recursively, right? Protons assemble into nuclei and creating atoms, and then atoms assemble into molecules, and then molecules assemble into larger molecules and bigger structures like DNAs, and those assemble into organelles, which assemble into cells, which assemble into organisms, into organs, then organisms, then us humans, and planets, moons, solar systems, same property. Things kind of aggregate, self-assemble, and you get a hierarchy of complexity, and that's sort of what a fractal is. It's kind of a self-similar, self-assembly kind of a process. And so nature kind of tends to behave that way simply because small things organize into larger things at different levels up a hierarchy, and there's no end to it. And so you get this fractal behavior, basically. That's sort of the intuitive explanation. Certainly it's true about all these phenomena that we've seen, right? Any other questions? Good question. Why does this happen? And so when Mandelbrot wrote this famous book called The Fractal Geometry of Nature back in the 80s, he's the first guy that said to everybody, wait a second, everything around us is fractal-like. So we better start understanding and analyzing things using fractals rather than Euclidean geometry and classical math. It's not powerful, it's not robust enough, it's not real enough to the actual real world around us to do justice to describing all these complex phenomena that we see, like erosion and avalanches and earthquakes and lightning bolts. These are all fractal. Even the coastline of a country looks fractal, actually. And there's fractal art, right? Earlier we said, can computers do humor? Can they do art? Can they do emotion? Well, they can certainly do art. These are all algorithmic art generated by computers using algorithms. And some of them you can sort of tell it's fractal-like. You can almost see the fractals or the Mandelbrot set type objects like this. But others you can't. And by the way, these are like 7, 8, 9 years old already. Today they're even more sophisticated than that. They get more sophisticated every year in terms of the art produced by computers. These are all, again, computer-based art, and most of these are based on fractal-like kind of computations. Some of them look like, so cool, like you can imagine in some modern art museum, some person, so these are animated, some person might pay, a good number of dollars for a canvas that looks like this, even though it just took an algorithm, half an hour to produce. It's hard to tell that, some of these were not made by humans, actually. And some of them it is, you can sort of see the 3D Mandelbrot set, like a type object right here. But others, not so much. They're pretty abstract, they're pretty creative. You can animate them. And again, this is almost 10-year-old kind of examples. There's computer art contests every year, and they select winners, and the judges are, of course, real artists, even the renowned artists, and so even art is now being encroached on by computers, by algorithms, by Turing machines. And sure enough, this reinforces what we've been saying this whole lecture, the Church-Turing thesis, is that everything that humans can do, computers can do also, at least eventually. And there's examples in art. I have a lot more examples. I'll just flash through them quickly. Okay. So if you want to know more about these things, about fractals, there's the Mandelbrot authored book. If you want to read one book about it, that's probably it, The Fractal Geometry of Nature, which explains why nature is so fractal-like, among many other things, including the mathematics behind some of the fractal properties and so on. This one has a lot of artistic kind of color plates focusing more on the elegance, the beauty, the aesthetics of fractals, and there's a whole bunch of others. And so the Church-Turing thesis, we started by asking, what does it mean to be computable? And we said anything that's intuitively computable is also Turing machine computable, and all these other systems are lumped together with Turing machines, namely DNA computers, billiards, Diophantine equations, of course, digital circuits, finite automata, cellular automata. Bottom line, we still don't quite know. I visited a particular museum. Anybody can guess what this museum is, by the way? This is a famous museum in Paris that shows works of Rodin. So The Thinker is a famous Rodin piece up in Sour, The Thinker. So this is Musée Rodin in Paris. So there I'm contemplating the Church-Turing thesis of all things. And any questions about any of that? So that's where we stand on the Church-Turing thesis. It's still alive. It's still not just believable, but more and more evidence is accumulating in favor of this thesis. And every day we see yet more evidence towards it. So that's pretty interesting. We have a few minutes left. I want to spend it on talking about context-sensitive languages. We mentioned them a few times. We never quite gave an example or covered them in great detail. But context-free languages have only one variable on the left-hand side of every production rule. But context-sensitive languages could have other things besides a single variable on the left-hand side. And context-sensitive languages can generate all the things that a Turing machine can recognize. In other words, they're as powerful as Turing machines in general, right? So they're outside the context-free. They can recognize languages which are not context-free. And I want to give you an example of how they might work, so you have an intuition as to how a context-sensitive language or grammar can do or be more than one that's context-free. Stuff that you can't do using a context-free grammar or push-down automata. So for example, design a context-sensitive grammar to recognize all strings of the form 1 to the n, 1 to the 2 to the n. In other words, two groups of ones across a dollar sign where the second group of ones is in length exponential in the length of the first group. So you have, for example, you can have 3 ones here where n is 3, but 8 ones over there. 1 to the 2 to the 3, that's 1 to the 8, that's 8 ones there. Right? So basically it's trying to recognize an exponential relation between the number of ones in the first piece of the string and the number of ones in the second piece of the string on either side of a dollar sign. How do you enforce or recognize such an exponential relation? A PDA cannot do this. A finite automata cannot do this. You can prove that using the pumping theorem. But how do you do it using a context-sensitive grammar? So here's a context-sensitive grammar. S goes to 1 ND, 1E. So N, D, and E are non-terminals. They're variables. The ones are terminals. And of course, the dollar sign is a terminal too. And sort of, I'm writing out the grammar here, and I'm kind of putting comments to kind of annotate the function of these productions. So this is the base case where it starts. It starts by spitting out a 1 here, a 1 here, and the two variables N, D, and an E right there. And I'm color coding them. You know, E is the blue rule. D is the purple rule, and so on. N is the green rule. So the N is a loop. It'll basically put a lot of ones. If you apply it many times, a lot of ones on the left-hand side and a bunch of Ds on the right-hand side. D is sort of a doubling rule. Basically, a D1 becomes a 1-1D. In other words, the D jumps over the 1 according to this red rule, and as it does so, it doubles the numbers of 1. The numbers of ones. In other words, it makes the single one a double one. Okay? Now, the DE is sort of the termination rule. It cancels the D against the final E here. And then finally, the E can go to epsilon, which means nothing more will be generated. You'll see an example of how this works in a minute. Okay? But that's the grammar. That's all there is. Look, it's not context-free. Why is it not context-free? Because there's a D here and a 1 here on the left-hand side of the rule. The D here changes to a 1-1D, not by itself, but in the context of a 1 on the right of the D. That's the only time this rule can trigger, is if there's a 1 on the right of the D here. That makes it context-dependent or context-sensitive. It's a D in the context of a 1 on its right can change to a 1-1D. Okay, so there's the grammar. I rewrote it here. Let's take an example. So S goes to 1 N, D, 1 E, like this first rule says. You got to start somewhere, and you start right there in this unique starting variable. And then this N, the underscored character or variable, gets triggered as a rule. So N, applying the second rule, becomes a 1 ND. So this N is replaced by 1 ND according to this green rule here. The D and the 1 ND remain there. Then the D1 is replaced according to this context-sensitive rule here in red into a 1-1D. Okay, and then the N changes to a 1-ND, and then the D1 can become a 1-1D here, and so on. Now, what is happening here, this green rule gets applied and spits out a 1 to the left and a D to the right. Then these Ds migrate over all the ones. They just hop over all the ones, and as they hop over every one, it changes into 2 ones, according to this red transition rule. A single one becomes 2 ones. So as the D keeps migrating over the ones, it doubles the number of ones going all the way to the end. How many get this behavior? Okay, good. And then it keeps going. And this N can generate yet more 1 to the left and a D to the right. So for every one it generates a D that then would double all the other ones to the right as they pass over the ones. And it can happen in any order. This is a non-deterministic kind of grammar situation where these rules can trigger in arbitrary orders, and I'll leave it up to you to verify that no matter which order you decide to trigger these rules, the net effect will be the same. The number of ones on the right will end up being doubled, the exponential, the 2 to the n of the number of ones on the left, n ones. And then what happens later? Well, the D's end up finally eating the hitting the E on the end, forming a DE pair, and the DE becomes just an E. So when the D hits the E, it vanishes according to this rule. So a D in the context of an E immediately juxtaposed to its right disappears. The D disappears, leaving only the E there. That's what this transition is here. So as the D's jump over the ones, doubling their number, and reach the E, they finally disappear. So the D's keep trickling down, doubling everything in their wake, and then disappear. And if you do this n times, you get 2 to the n ones. How many get that? Yeah. And that's how this grammar works. And at the end, this keeps going. I'll just show you all the transitions, the remaining transitions. At the end, what would happen, the last D would reach the E and finally disappear, leaving only the E there. And then the only rule it can trigger if you just have an E is not this rule, not this rule, not this rule, not this rule, but only this rule. And the E will become epsilon. The epsilon will vanish, and you've produced this string of 3 ones and 8 ones with a dollar sign between. That's 1 to the 3, 1 to the 2 to the 3, and that's a string in this language. And every single string in this language could be generated this way. How many get all this? Okay. Any questions about that? So this is an example of a context-sensitive language, not context-free, using a context-sensitive grammar, not a context-free grammar, context-sensitive grammar, to produce a language that's not context-free, but is context-sensitive. And you can sort of see how a Turing machine can be simulated with a grammar now. The read-write head position will be in a context of a character. We'll either swap with it or not and change that character, and you can convert every move of the Turing machine into a context-sensitive rule. How many can see that? Yeah. Right? So the read-write head, whether there's a character, a particular character on its left or its right, can move over the character or move to the other direction, and meanwhile switch that character to another character. And so a context-sensitive grammar can simulate an arbitrary Turing machine in this manner. And this partial form is the tape of the Turing machine analog. How many can see that? So as this grammar evolves and keeps swapping things around and changing things, it's like the Turing machine doing its job, basically. So a Turing machine can automatically be translated into a context-sensitive grammar that would have the same effect as a Turing machine. The grammar will produce all strings accepted by a Turing machine. It's an if and only if. So now you know why context-sensitive grammars are so powerful and why we delineated them and distinguished them from Turing machines, right? So grammars can implement arbitrary Turing machines if you allow them to be context-sensitive. Any questions about that? All right, the midterm has been released, as you know. You should be working on it. Some people have already turned it in. We appreciate that. You have until Saturday, 6 contiguous hours. You can work on it at your leisure. And it should be easy if you've done problems all along, which most of you have, so there should be no surprises there. All right, see you next time. Yeah, just a second. Can you do me a favor? Press the off button on that camera and bring the whole tripod down here. I appreciate it.
So I've had an issue with the midterm where I accidentally downloaded it on Saturday when I had I didn't see your email at first about